This is the Cordasa software. You can go to corrosiondjinn.com, and one way of thinking about it, it's an electronic version of the mill standard, and you can see all the data. You just go straight to the substrates there, and you can click and see the pages and pages of data that we have, and also a lot of coatings. So, but if you have access credentials, you can then use the corrosion analyzer. So what we do, we have different environments, 3.5% sodium chloride, kind of a maritime environment. There's also the mill standard 889D environment, which is artificial seawater. So we have all that mill standard data, and we can compare materials, material 1 against material 2, and you can see here how we're making the choices of that aluminum 7050 structure, and then considering what a stainless steel fastener would do coupled up against that structure. So I have quite a lot of different stainless steels available. We click them, we have this substrate designation, coating and treatment. We can look at different treatments. It pulls the polarization curves, and there's your materials, the aluminum, which in this case is anodic, and then over here we have the stainless steel, which for this case is cathodic. But the guts here is down in these tables. We have the self-corrosion rates of the materials, but the kicker, of course, is when you couple them, and that corrosion rate is much, much higher. You can see it's in the red or pink zone, or number 5 there for the mill standard. We can copy that very quickly, and we have a new group of material 1, material 2. It self-populates, so now we can just swap out the stainless steel for the Ti-6-4. It's very quick. It's just a click, 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 and run the analysis. Pulls curves again, and this time the titanium Ti-6-4 is cathodic, and the corrosion rate is much, much less on the aluminum. Okay, so titanium is shown as a better choice, but maybe titanium is a little bit expensive for the asset. What other things could you do? Well, we could perhaps apply a coating. Let's do a zinc nickel coating on the fasteners. So it's no longer seeing the stainless steel, it just sees the zinc nickel. So we choose that as a coating. We have a dip salt coating here. Now you can see the aluminum is cathodic and the coating is anodic, so it's sacrificial. So the corrosion rate here, although it's it's low, it's the corrosion rate of the coating. You got to remember that. So it gives you an indication of that consumption rate of the coating. But the key thing, of course, is that the aluminum is experiencing no corrosion. Now the mill standard makes the assumption that the area ratio of anode to cathode is 1:1. But what we've done here, we have a facility where we can put in a different area ratio. So let's say the aluminum is 10 times the area of the fastener, which is quite likely if you've got small fasteners. And you can see that the corrosion rate here is considerably less. It's like 56 microns, whereas it was a couple of hundred before. So you can take into account the area ratio. You can't do that in the actual military standard. Okay, so what did we do there? We just very quickly did some trade studies. We had 4 material couples. We coupled aluminum with a stainless steel, aluminum with a Ti-6-4, then we considered a coating, and then we looked at the difference of what would occur if we had an anode-cathode ratio that was non-unity, and we have the summary here.